first event, or we were just looking at some of the press releases, and the first one that we found was this wonderful image of a flocculent galaxy. So I'm sure you're familiar with the common perception of what a galaxy should look like. Even our own galaxy has these nice, well-defined spiral arms, and you can see this in many, many galaxies. And this is thought to be uh, the standard form of how galaxies are formed, or standard structure of how a galaxy forms. But in a flocculent galaxy like this, you have a lot of dust, but no clearly defined spiral arm in the outer disk. Whereas in the inner disk, you have virtually no dust, and all of these stars are dust-free. It's just a very nice image, and it's we just want to talk about what this means. So yeah, there's no spiral arms, but because there's so many young stars, massive young stars in the outer disk, then you have a lot of dust and a lot of stellar winds and things like that that populate this outer disk with dust. And yeah, Elena, do you have anything to say on this one?
No, I don't.
Okay, you can hear me though, right?
Yes, yeah, I can.
Just to make sure.
Yes, but still, I want to ask a question.
Yeah, sure.
Like, so why it looks like the feathery? Is it because of the some physical process there, like magnetic fields or some pressure difference? Do you have any idea?
This is the just a high population of these massive stars, and it's not
Mm-hmm.
really confined to these spiral arms.
Oh.
In the galaxy like our own Milky Way,
Mm-hmm.
you would have these spiral arms that have these giant, massive molecular clouds.
Yes.
And if you look at observations, usually radio wave
Mm-hmm.
observations of other galaxies, and then you can see the giant molecular clouds in radio waves, and you can see that this follows very nicely these spiral arm patterns.
Mm-hmm.
But I don't know how this looks in radio, but I don't think that you would be able to pick out a spiral arm. It'll be very random at best.
Yeah.
Yeah. So the next one was this is a very nice sort of paper. So for a black hole, I'm sure that you've heard of Hawking radiation, which is a radiation that a black hole emits. But for a spinning black hole, there's a theory by Zakov-Zeltovich that you can actually harvest some energy from the spinning black hole. If you were to drop something, if it was co-rotating or rotating at just the right rate, and you were to drop something inside the black hole, and then you could recover something at a higher energy, higher velocity, I guess, in that case. But so this was a theory for how you could amplify light pretty much when it accelerates past the black hole. And then you can kind of harvest energy from the black hole, harvest its Hawking radiation. Um, so that's a nice theory, but it's very hard to verify this. First, you'd need a black hole, and you would need to make something that would spin at just the right rate. And I think the numbers I heard that it would have to spin like 1,000,000,000 times per second. And at that size, that's very, very large. So as kind of, there was a team in Glasgow, and they wanted to kind of test this, but they wanted to use acoustic waves rather than light. So they used acoustic waves, and then the suppressor, the sound suppressor that they used to kind of reflect the light, um, that didn't have to spin at quite a high rate. It still had to spin at a high rate, but not a billion times per second. And then they were able to verify that the reflected sound that they get from this device was higher than the one that they sent in. So it was very nice paper, and it's a nice result.
Correct. We have a question, and it asks like about the previous result, like about the feather galaxy,
Yeah.
and the question was like, why there is no stars near the core?
Yeah. Near the core, that's all very, very old stars. Um, so they might have, well, they probably did have a lot of dust at that time, but then it just reprocessed a lot faster than the rest of the disk. So whatever dust they have expelled in stellar winds or anything like that had already formed another star. So then you don't get the dust in the center of this type of galaxy. Yeah. I think there's a bit of a lag from YouTube, so
Yeah.
maybe I go a bit too fast. That's okay, but I'll answer any questions whenever you pose them. So thank you.
If anybody have something to add with that from the community.
I'll say no, I guess.
Okay.
That's fine. But yeah, did you have any comments on this one, Elena?
Not yet.
Not yet. No, I meant you yourself.
Oh no, sorry, I don't have.
No, that's fine. But yeah, this is a very nice image, and
Yeah,
so
it's really good. Yeah, it's a really nice result.
I like this result. You can find this article in Forbes, and they have a nice video that also explains how they set up the experiment, and it's a bit technical on what is the difference with these reflected waves. But if you can understand it, then props to you.
I hope we will add all these links in the description box so people can check.
Yeah, that's a good idea. I will do that. Yeah. So another result was that it's been known for 20 years or so that there's chlorine on the surface of Mars and chlorine in the dust of Mars or in the atmosphere. But there's often these large dust storms. So like, I think once every 2 years, there's a global dust storm. And then once every year, there's regional dust storms. And then every so often, there's a dust devil, small dust storm. And because there's so much, the atmosphere is so active and there's so many storms, and this kind of mixes around chlorine. And what this does is, it kind of mixes up. It can even bring up some chlorine that's kind of just below the surface of Mars. And then this has some implications for life on Mars, because the chemical reactions that are associated with chlorine, and it's a nice result for the SETI people, the search for extraterrestrial life. I mean, we didn't find life on Mars, but it's a nice result for them.
Yeah. So you're telling like this can be a like you say, like water or life. So chlorine and on the atmosphere says that maybe there is some life, or there was.
Yeah, or at least
Okay.
that would promote the development of life.
Okay.
I have a question. So this
Yeah.
chlorine is produced in the atmosphere itself, or is it in the surface or within the rocky part, and then it's transformed to the atmosphere?
I think it's a bit of everything. There's definitely chlorine in the soil and in the atmosphere. I mean, that's how they would detect it initially. They haven't have a soil sample or anything, but um, it's just that with these giant storms that are existing on Mars, it promotes some more chemical reactions and things like this.
Thanks.
Good.
Yeah.
Um, yeah, so that was a nice result. And diamonds in the sky. Yeah, so this one is a bit different. So if you think of Neptune or Uranus, these are planets very, very far from the sun, and the surface temperatures are very, very cold. But because it's such a massive planet, it has a dense core. So near the core, it gets very hot and very dense, kind of counterintuitive. So the, not all of Neptune is super cold. At some point, there's the gas, yeah, the state of the gas because it gets so dense, and then the temperature gets so hot. So the one of the thoughts were that in these hot, dense atmosphere, so that should be inner atmosphere, carbon just naturally goes into a diamond. The chemical reaction happens very quickly, but it was hard to kind of verify this. It was, yeah, kind of thought of, but recently there was a way that they finally got the test conditions made on Earth so that they could actually test whether or not this was possible.
Mhm.
So this article was in Science Alert. But yeah, that was very nice. So possibly in Neptune and Uranus, I don't think they said anything about Jupiter.
Mhm.
Jupiter is a bit different.
Yeah. So maybe we have to plan next mission to Neptune and
Yes.
take some diamonds and come back.
Right now, I think only Voyager 2 went past Neptune.
Yeah.
But yeah, it's very far away. The last planet in our solar system.
Yeah. Because we kicked out Pluto.
They did. Yes. And for the next topic, solar magnetic fields, which is always fun. So at least me as an astronomer, what I learned in school was more how to treat the magnetic fields when you're kind of doing more space physics or physics at a planet, and the interaction with the solar magnetic field and the magnetic field of the planet. And so you just kind of consider that these magnetic fields just emanate from the sun. They emanate in spirals, but that's due to the rotation, and that's not what I wanted to talk about. But um, the idea was that these have kind of open field lines, so to speak, which is very counterintuitive for physicists because there are no magnetic monopoles. We haven't discovered any. So every magnetic field line has to kind of go in a loop. They can't really diverge.
So, like in simple terms, you mean like every time you need a north and south pole, right? You you when you say like open
With
field
a,
lines, you mean like
with a,
only north or south as
yeah,
visible.
yeah,
Mm-hmm.
kind of, yes. So for a dipole, this would be more like the Earth's magnetic field, where it
Mm-hmm.
just kind of goes in a loop. You
Mm.
have a north and clearly defined north and south pole. But for the sun, that's a bit different. So what this study was working on was during a total solar eclipse, take a picture of the sun or what you could see of the sun with the moon in front of it. And you can see these well-defined magnetic field lines that are kind of emanating from the sun, kind of confirming that perspective. But this is not existence of a magnetic monopole. This is due to the stellar winds and how the plasma kind of emanates from the sun. And if you can look very closely, it might be a bit hard to see, but best way for me, at least, when I'm looking at it, if you look at 2008 and 2019, they look very, very similar. I mean, a few differences, but the basic structure is the same.
Yeah.
And the reason for that is because that there's an 11-year cycle to the sun. So it's, we call it solar activity. So the amount of sunspots, which is due to the surface magnetic field, this kind of goes on an 11-year cycle of when it would be active and when it would not be active. Yeah. Or sorry, 11-year cycle. So 7.5 years. Sorry, 5 years before it becomes inactive. But anyways, so you have the same magnetic field structure here, 11 years apart. It's very nice to see.
Yeah, and during this, like after this 11 years, and the poles of the sun will change, right? That's what happens usually. So the north pole becomes south and south becomes north, like that, you mean?
Yeah.
Okay. Nice.
And it's just very nice to actually see this from an observation. But they can only do this during a total solar eclipse, so this is rather difficult. You can't take a lot in a row. But it's nice to see this sort of evolution of the magnetic field of our sun. But yeah, this is very useful for studies in magnetism in stars. Although, right. So the last one that we want to talk about was dimming of Betelgeuse, Betelgeuse. I've heard it pronounced many ways. So however you like to pronounce it, then that's fine for me. But I don't know if you've been following space news last year, but everybody was, at least in the public data release, there was one that, because Betelgeuse started dimming, so then the public data release was that this might be indicative that it's about to go supernova. But when an astronomer says it's about to go supernova, I mean, that can be like thousands of years away. So that doesn't mean it's going to happen in like the next day or anything like that. But the public got a hold of this, and then everybody was worried that the Betelgeuse would be going supernova or something like that. And then there's another study that came out and said, no, there's actually dust. There's too much dust that's being expelled from Betelgeuse, and that's what's dimming the light.
So you mean the dust is obscuring the light coming from the Betelgeuse, and which we cannot see. That's why we are like,
So
okay.
It's kind of shrouded in dust. So somebody took a radio wave observation or infrared observation and like focus talk that you just listened to. They noticed that this dimming was also seen in the submillimeter wavelengths. So now they're proposing that maybe no, it's not dust that's causing the obscurity. It's these large, massive sunspots, which is due to the magnetic field on Betelgeuse. But this was the theory that they came up with. I think it reached its minimum brightness in February this year.
Okay, like the
Now I
sun
think
have
it's coming
minimum.
back up.
Okay, so sorry, like you mean like sun have minimum activity and like maximum? The same way even Betelgeuse have a minimum and maximum.
It should, yes. I don't know if that's what they meant by it.
Mm-hmm.
Betelgeuse is a red supergiant, and these
Okay.
can be kind of volatile and they can be rather variable,
Mm.
just an inherent property
Oh.
due to the kind of always uh, increasing and shrinking in size.
Mm.
So it's hard to make that claim right now. But yeah, I don't think what they observed was the magnetic or the activity brightening and dimming,
Mm-hmm.
but they claim that this was instead due to the solar spot.
Okay.
And for a very, very bright star to have such a large solar spot that it would decrease in how much light it's producing,
Mm-hmm.
that has to be a very, very large solar spot.
Mm.
Yeah. Do you have anything to add?
Oh no, I don't have. Is
No.
anyone else
That
have
should be good.
something?
No, I think you described it pretty well.
Good, good. Oh, yeah. So
Mm.
this is what we have for now.
Yeah, there is a question from YouTube, and it asks like how solar winds are related to magnetic fields.
Right. So yeah. So sometimes you can kind of get a solar flare or these smaller flares that are kind of emanating up like a rope kind of this plasma that's on the surface of the sun. And that rope is because there's kind of magnetic field loop. There's actually a very complex magnetic field on the surface of the sun. So what I didn't show from this paper was that they had another image that was more zoomed in, and then you can see a lot more of the structures right at the surface of the sun. It's very complex, but so basically what happens is that there's this magnetic field loop that kind of starts to emanate from the surface of the sun, and there's all this plasma from the surface of the sun that's confined to this loop. This is called the flux rope, if you're interested. And then eventually this loop kind of reattaches, but there's still a lot of plasma here, and then this plasma gets expelled, and that is the solar wind, and that's the plasma from the sun that is kind of emanating away. And in these images, this is kind of aligned with the north and south pole of the sun. So it's also rotating, and you can see a very strong magnetic field here in its plane of rotation. So as it rotates, and then you can assume that it's doing a lot of these solar flares and expelling a lot of solar wind. So the theory for the magnetic field just coming straight from the sun, or these open field lines, is because it kind of, you can kind of follow the magnetic field based on this, all of this solar wind and this coronal mass ejection. That's what this plasma is called when it's expelled. So yeah, that's how you can kind of trace the magnetic field, just by the plasma. And then eventually this plasma reaches Earth, but thankfully we have a magnetic field on Earth, which protects us. So the plasma starts to interact with the magnetic field on Earth, and then it starts to follow the magnetic field to the North and South Pole on Earth. And then that gives us an aurora because it interacts with our atmosphere. So northern lights or the southern lights, that's what causes that.
Oh, that's
And then
nice.
there's more to it. I mean, some of the plasma doesn't necessarily interact with Earth directly, but it has too much momentum and it follows to the tail of Earth. And then this is called the magnetosheath, and then it kind of recombines and it's expelled further. But the basic point is that our magnetic field can protect us from that.
Nice. I hope the person who asked the question got enough answers. And if anybody
sorry.
else have questions to ask,
I
then you
have
can.
one.
Yeah.
My question is towards Betelgeuse, and I want to know what exactly they mean with its dimming. I mean, is it like the average flux they get from this star during a period of time that gives this conclusion that it's dimming, or what is it? Because we know that the red giants are in the phase of variability, so they luminosity is changing in the periods of from some days to like 100 days. So what do they exactly mean?
Right. So why it was so perplexing to us was just that Betelgeuse for centuries or something like this was always the like around the 10th brightest star in the sky.
Mm-hmm.
And then last year when it started to dim, it became not even in the top 20 brightest stars in the sky. And it was just a bit confusing why it all of a sudden started dimming, which I think is still confusing that if you have this sunspot theory that that should happen at a regular occurrence as well. But anyways, this is the conclusion that they came up with.
Yeah, but this suddenly it means like for a couple of days that the luminosity
Well,
was so low, or even at the moment it's
it
not
was
glowing as before.
it was
Uh,
dimming. It was dimming. It started dimming last year. I
like,
forget what time.
can I say like it's
Sorry, you
in
go ahead.
October? Yeah, it's
Oh,
in
yeah.
started like in October 2019, and it's like uh, till April 2020 kind of, and it was like 40% of its normal value. The luminosity went like 40% of its normal value, and that's why it's like suddenly we got notice. And it was a surprise.
Okay, but isn't it the period of its variability? No, it's very
No, it
longer than 100 days. It's
yeah,
still
but
in red giant phase. Yeah.
yes. So previously it never showed this kind of variability, and it
Mm.
suddenly showed
Mm.
at this time. So
Can
everybody
I
was
show the light curve
Oh,
to
yeah,
help?
yeah,
sure.
sure.
Yeah. I'll stop sharing. Yeah. Do you want to share?
So that is actually some like some continuous measurement. So you see it is variable,
Uh,
Oh,
but you see the other estimate is streaming
oh no.
again.
I'm very sorry, but it's choppy again. Okay.
Just look.
Yeah. That seems somewhat more regular now. That. Yeah. Okay. Perhaps it's more regular than I thought, but you could see at the end there was a very large dip.
Yeah, it's kind of the lower limit is also decreasing.
Yeah. So it's a bit strange that it starts to get so dim all of a sudden, but yeah, so
Yeah, that was a very useful information from Volker. And thanks, Volker.
thank you so much for sharing that.
Yeah.
Yeah, I didn't look for that graph. That's very useful. Let me just share this again. So that's sort of the dimming of Beetlejuice. So that I think that was last week. Space.com made a press release on that. But that was sort of the end of the news, AstroNews. Feel free to ask any other questions. We're happy to answer. And if not,
Yeah, we have one request to the paper regarding the solar eclipse.
yes.
Yeah, so someone is asking for the link.
Oh yeah, sure.
Yeah, so
or
we will
if-
put all
Or
of
if you know ADS, then you could search on ADS, Boy et al. 2020. But we'll send the link, or we'll put the link in the description of the video when we post it. There are some things that I should probably cut out, where I'm just kind of talking during the technical difficulties. But other than that, yeah, we'll put it in the description of the video. And besides that, follow us on Facebook and Instagram for updates for games, not really games, but quizzes. You can try to test your knowledge of astronomy. AOT Cone is our handle on Instagram or Facebook, also on YouTube. You're here, so you know that. So we don't know what our August presentation will be. I don't know what it will be on. It might be in German. I'm not sure. But we'll let you know. Follow Facebook and Instagram to find out. But we do already have our September presenter finalized. And so we have Professor Michael Kramer, who will talk about pulsars with us. It should be very nice. And yeah, that's all we have. So thank you to everybody who attended, or who stuck through all the technical difficulty. We really appreciate it. Do you have anything to add?
No, I don't have. Thanks to everyone. So we will see you on the next event.
Yes, next event in August. It should be the first week of August, I think.
Yes.
But you'll see us online, not in person. Okay. So,
Yeah, that's for it now.
yes. Thank you.
Thank you.
Thank you.
See you next time.
See you next time.
Yeah,
Bye-bye.
good